Good afternoon, everybody, again, and thanks for deciding for this session rather for the cake and the coffee. Appreciate it. And yeah, well, then I have the pleasure to get the first part of that session, and then I'm going to hand over to our friend here for the next part, and then we're going to take it from there. All right, so my name is Krueger. I'm from Intel Corporation, and I'm in our software and services group, responsible for IoT security, and I'm primarily focusing on the EMEA market. That's why I'm based out of Munich. But the rest of our our security guys, which is around 300 in the Center of Excellence I'm part of, are across the world, primarily in the US. And I have the pleasure to talk today about some of our new services, as well as how we are basically taking frameworks like IoTSF and applying those principles to technologies we are providing for our customers. And since we are a member of IoTSF, obviously, and participating in best practice guide and so on, I personally think that it's very valuable. And like other foundations and standardization work, I think that is an important piece to make sure people are able to consume what we are producing. And during the morning, I had a couple of discussions with some folks of you and others, and we believe, we actually agreed on the fact that security is not really a technology problem in general. It's more a problem of how you consume it, because we have so much technology, and whether it's an ARM chip or an Intel chip or RISC architecture, whatever, there's a lot of technology, but it's not very effectively consumed in the next layer or in the next part of the supply chain. And so at the end of the day, customer gets a product which has no security at all, even though the underlying infrastructure has a lot. And that's something we try to change as well with activities like the IoTSF. All right, legal disclaimer, don't need to read that. It's the usual legal stuff. And I skipped that slide that just marketing likes to put in something like that. But, well, I think we all know what the problem is. And we all know that we need to do something about it. So I'm gonna skip that real quick. As I just briefly touched already, one of the important points for us at Intel is really making sure that we provide security technologies and capabilities which are relevant for the industry across the different verticals, as well as that it relates to activities which are coming out of standardization bodies or foundations like this. Because at the end of the day, we are doing these integrations and invest money and time and effort in security technologies as part of our platform to make it a greater place, as our CEO always calls it. And that's actually how I think we as an organization look at it. And IoTSF in particular is a good example of how these things then come together from consumer or customer perspective, if you're a manufacturer or if you're a system integrator, how you consume what we are in putting in our platforms. And that said, we have been working in the last couple of years on various programs and projects where we've identified what type of requirements or actually what type of use cases customers have, and mapped those towards technologies we have in our portfolio. So it's really guiding the customers on their use cases towards what we are providing. And there are other standards. For example, we are also actively working with Industry Internet Consortium, for example, in the United States, more focused on industry and energy. But they are also creating requirements which are similar to what IoTSF does. And I think there's also an active discussion now ongoing between those two to exchange information. All right, so how does this look like really from architecture viewpoint, and then we go into the details a little bit when we look at security from Intel. So I started actually with IoTSF requirements, which we all agreed on and put in our working group 1 best practice guide, where we have requirements identified for device manufacturers or system integrators to validate their supply chain on or validate their products on. And those are pretty standard requirements. I mean, there's no rocket science behind that. It's just a matter of how you consume those. And so there are requirements around encryption and key management. That's always one of the things you have to do. You always need some sort of integrity and security which is tied back into hardware, because they are true root of trust. You also need identity, especially for IoT, because you want to know on whether the thing you talk with or you talk to is legitimate. And so these are very basic requirements if you think about them. But to implement them on all sorts of devices and across an entire ecosystem is rather a challenge. And so what we derived, not from IoTSF in particular, but generally out of standardization activities and our own research, are certain security usages or use models where we take those requirements and map them into a technology implementation, let's say, or in a use case which is underlined by technology. And so, for example, if you want authentication and authorization, you need a platform which allows you to do that in an appropriate time. So you need accelerators, you need crypto engines, you need hashing engines in a way that they perform fast enough to get this in the time and in the manner you want it. For application integrity and authenticity, there are really needs to extend that trust from the hardware into your platform, into your software, and eventually into the services if you take the whole picture. And encryption and key management is one of the topics we historically been very active on. Also for counterfeit protection, what we've been hearing a couple of speeches here today, because Intel chips are copied a lot, or parts of it. And we need to make sure that our customers are using legitimate equipment like DOE or GHCQ, or in Germany, a BS government organization, and so on and so forth. So that said, what we've been working on actually for the last decade is a 4-pillar platform, let's say, that the commitment we give into the industry is that all our platforms going to have those 4 principles. These are our security essentials, if you want to call them this way, that every chip you buy from us, regardless of what type it is, and whether it's a very small one you'd use on the edge in a small device, or if you take a dual socket Xeon with, 12 cores each in the data center, they all have the same 4 principles. And they are associated to actually those security usages, and then can be used to comply to certain requirements like the IoTSF is calling out. And to just briefly mention them, I go into those into detail, is on one hand side hardware and software identity, so that you have a really true identity, but not in the way that it's allowing you to trace something, so it's anonymity. It's an anonymous identity, which is very much important for us. Then we provide a lot of technologies around platform integrity, how you ensure that your whole system comes up properly, that you extend the trust into higher layers in the architecture. We also provide what we call trusted execution environments, which allow you to run code in a secure place, so that you can, as a developer, you decide what part of your application runs in that trusted execution environment. It's not us. We give you basically the tooling, and what you do with the tooling is really up to you, but we guarantee that everything which runs in that TEE remains there. And in our latest generation technology, we actually make sure that the data are encrypted on the entire platform. So only the CPU itself can decrypt the data. So it's a very high level of security you can achieve by running certain elements of your code inside of that TEE. And then crypto and protected storage, we put that together, even though for crypto I could have a list of 100 different things, what we do in crypto in terms of acceleration, that we have all sorts of algorithms as part of our platform, whether it's ECC, SHA, hashing, this is true number generator platforms, and as well as those crypto functions to accelerate and generate cryptographic material. We have also the storage where you can store those. And this, in our case, it's a platform trusted platform module, so a TPM, but it's not a discrete TPM as a physical chip, it's a firmware TPM. But it's implemented in a way that you can use it as a TPM, has the same interfaces, is certified, and can be serving as a protected storage. And so, as I said, one of the important pieces now is making sure that all the magic we have now is going to be consumed by the ecosystem. And I have just three prominent examples here, cloud vendors, but it could be anybody in the ecosystem. And that's what we provide through our unified application security API, which is an abstraction layer. So instead of using the technologies which are part of this underlying framework, each by each, by which you need always a specific software development kit, which has specific APIs, and you need to train your engineers to learn how this works and implement it. Instead of doing this, we've abstracted those use cases and usage models into an API. So as an example, if you want to, for example, generate RSA key pairs, well, you write approximately 5,000 lines of codes if you do it yourself. And you need to generate the keys, store them somewhere, you need to implement the algorithm, and so on and so forth. If you do this with our application API, you do this in 3 lines of code. You say you want this function, you call it, and you wait for the return. And we select out of the API the strongest security principle available on the platform. So the developer don't need to worry any longer whether I use technology A, B, or C. They just say, I want this function to be executed in the most secure manner. And we enable that by providing such an API. And on top of this, to take it to implement this across the entire supply chain and utilize security properly, there's one particular problem, and that's one of the main topics I wanted to cover today, is how you get devices into operations. If an ODM develops a device and manufactures a device, then the next one in the supply chain has to open the box, put some secrets on the device, and then ship it to the next one in the supply chain, who's then using that secret to authenticate to something. Or you have to give your supplier your secrets, which is unlikely to happen. And so in order to mitigate that need to exchange secrets to an untrusted system, and the need to open the system and provision it manually, we've been implementing what we call now Secure Device Onboard, which is a zero-touch, just-in-time provisioning service from Intel. Meaning that, take an example like Vodafone or British Telecom buys 5,000 gateways, so from Dell. So Dell would run a specific process in the factory, which we help them to do, which is in establishing a universal identity, if you want to call it that way, on the platform. And then these devices are not shipped to BT any longer. They go straight to the end customer. And the only thing they need to do is switch it on. The rest on the onboarding is going to happen automatically. I come to this back in a little bit later. But this is an important service for us because it makes sure that from reset on, the device is being brought into a trusted state. You can use these 4 principles to bring up the platform trusted and secure. You can run your application secure and trusted. You can generate cryptographic information and store them properly. And before you do all of this, you need to get your device into some servers. And that's where we close the loop, basically, with our service here. We also have another type of service we are providing, which is around attestation, which allows customers or end customers eventually to verify remotely that the device is coming up with an owner-defined stack. So the owner decides, this is my stack of firmware, BIOS, bootloader, kernel, application, and this entire stack is measured in the TPM, and we provide the additional backend components to get this data, compare it to whatever is the golden reference, let's say. And so you can attest during lifetime that the device still has the legitimate stack. And that goes beyond or below the operating system, which is important for us. Because everything below the OS is more difficult to detect if something goes wrong. But it's very attractive for adversaries to attack BIOSes, for example, bootloaders, and do something different with the platform. All right. So getting from there into we are silicon manufacturer, so for us hardware is an important topic. But we really believe, and I think we hear this today and during the work with IOTSF, I think we all share the same opinion that it needs to be designed in. We need to start with something at the beginning. And since we as silicon providers are in the responsibility, let's say, to provide technologies to do so, we basically taking that responsibility on. So to walk you through those capabilities real quick, is really on first-hand side is really our accelerators. And as you might know, we have been acquiring Altera a couple of years, I think it's 2 years now back, with their FPGA portfolio. So that's another acceleration possibility. But generally, we are providing, and the list is not complete, just goes on for many, many more lines, really a lot of security acceleration technologies to make sure that if developers use crypto, which we want them to use, it is done fast, as quick as possible, without affecting the system. And I remember 10 years back, as we were talking about full disk encryption on laptops, everybody was saying, well, that's going to take forever. And it was. You couldn't do full disk encryption because it was so slow that the CPU was consumed 50%. And then we brought out AES-NI, AES acceleration in hardware, and all of a sudden the full disk encryption was just neglected performance impact. And since then, it's like a standard that every enterprise uses full disk encryption. So that's just one example how accelerators help to consume technologies we want them to use, like encryption. Same as for network. If you want to do real-time networking with TLS, well, you need accelerators. Otherwise, it's not going to be real-time networking. It's going to be non-real-time network. And so that's a very important topic for us. And with FPGAs, we also provide there in another design possibility that you can use this besides other architectures, not just Intel if you have an FPGA, and you even have more performance with an FPGA than you have with a CPU, because you can really implement a very complex algorithm in a very efficient way. Taking on basically the next step of what we're providing are additional technologies which are part of our SoC, and they are primarily consumed through our partners. So this is usually a technology you would not necessarily use as a customer yourself, because we are making sure that operating systems are consuming those. For example, Microsoft or Linux kernels, they basically have those technologies enabled by us. So we are making sure that there is the possibility to enable these capabilities in those standard operating systems, let's say Linux, Android, Microsoft, name 3 of them, and also a couple of RTOS systems like a QNX or Green Hills or others. But still, why I'm pointing this out here is that this is always an optional features those SIs or OEMs then going to have to enable. And some of them require some activities to be completed at the OEM level, where you need to fuse in some keys or you need to pop some fuses with certain data points. So it's up to the next one in the supply chain to request those capabilities to be there. When we are in the Microsoft world, well, it's easy because Microsoft enables a lot of things standard, but in IoT there is no Microsoft, or not much, let's say, depending on the size of device. And so it's really up to the next one to request those capabilities. Another aspect is virtualization, which we see a lot of activity also in IoT nowadays, where vendors want to remove dependencies between their actual application and services and the underlying hardware for all sorts of reasons. And so like we have virtualization in data center, that's all great, but none of what we've learned in the data center is going to be relevant in IoT. That's very, very hard for the industry to understand. Because I think, well, I use hypervisors and VMware and KVM in the cloud, so it will work on my device equally. Well, it couldn't be far from reality than that. And security needs to be implemented in a much different way when you virtualize outside of a data center. Because you have less controls. You're not in a cage, you don't have physical access controls necessarily. The thing sits somewhere in the middle of nowhere. And that's where we provide all sorts of security-related functions which are making sure that certain applications running separated from each other. Then one of our most or very important topics around identity is our enhanced privacy ID. That's an Intel invention, it's 10 years ago, but by now we've standardized it in TCG and ISO because we believe that for IoT we need a universal anonymous identity mechanism which scales to the volume which is forecasted, depending on which numbers you take, but they're going to be a large number. And so PKI is not going to scale there in our opinion because you have a one-by-one relationship, you need to maintain all of this, so it's a hell of work. And if you have a revocation scenario, I don't want to even think about it. There are some numbers from Gardner and Forresters and others which did some estimations on how much revocation costs. And I think some of the presenters on the panel this morning was also referring to those. It's a huge cost. And with traditional PKI, you have to have a very good revocation strategy, which unfortunately is not always the case. And with Appit, we have a different cryptographic theme, which also ECC based, and in its next generation, eventually post-quantum secure, which is anonymous by default. So to anonymize something which is not is very hard. But to de-anonymize something which is already anonymized is very easy. And so if somebody needs identity which is not anonymous, no problem. But if you don't need that identity, but you need a proof point that the device is authentic, then Appit is a very good theme for that. And we have been working with many partners, so this is not exclusively to Intel. So we have other partners like Microchip, Atme, Renesas, Infineon, you just name a couple of them here in Europe, which are using Appit as well in their platform. So they are selling their products with an Appit-enabled system so that the ecosystem can consume Appit for other use cases. When we look into platform integrity, this is one example of what we are doing there. In the first place, we are very actively driving open source and open standards in terms of how you initialize a platform, whether it's with UEFI, with U-boot, or with Core Boot, which is Intel's preference, let's say. We also provide additional technologies which allow you to validate that your BIOS is actually the BIOS you want to run, and if it's not the BIOS you want there, then the system doesn't boot. So there are all sorts of use cases we implemented with our silicon capabilities to make sure that the platform boots into a known good state instead of something which is unknown or it's vague of what it really is. And with this extreme lifetime of the devices, 10, 15, 20, 30 years, depending on industry, we need to make sure that the device always comes up with a trusted stack. Otherwise, we can't trust the data it generates and provides. And I have just one sample view on how this could work with our bootguard technology, which is validating the initial boot block of your BIOS. And then you have, for example, Core Boot, and you take, for example, UEFI payload, and then you take it from there into your operating system with bootloader, without bootloader, whatever you build there. But important is that the first part is trusted. And underneath, we always have our firmware TPM, our platform trust technology, which gives you the place where you can store your secrets properly and generate keys properly, because that's what a TPM does. So that's a very important piece for us, and we really take that on as our responsibility to provide the technology so that you can build trusted platforms. So speaking of our platform trust technology, this is basically how it looks like. At the end of the day, the ones of you working with TPM, it is a TPM 2.0 based on TCG specification 1.0.2. I think these are the latest. And it's basically providing the same interfaces than a TPM. For a software developer, there's no difference. They just use the same drivers, the same interfaces. And we have made sure that all the Linux kernels are, since many, many years, are supporting these interfaces, that they are the appropriate drivers also for TPM 2.0, because there's a very small adoption of TPM 2.0 at the moment, because there are not enough tools. If you use standard tools from Linux, they're all designed for TPM 1.2, but it's broken because SHA-1 is broken. And so we are emphasizing a lot TPM 2.0 and investing a lot into the tools around it, so that you can use your tools you're used to in the Linux environment to use OpenSSL or using TLS connections or using crypto functions and so on. But instead of using a 1.2 TPM, it's a 2.0 and in firmware. Trusted execution environment. This is also a very important topic for us across our portfolio. So we have a TEE on all our platforms. And there are two flavors we have. Basically, one is our well, it's not really legacy. We have a good, a best, and a very best, or best, or good, or best. I don't know what you would describe it. Level of security with those TEEs. The first one is our dynamic application loader, DAL, which is providing you such an environment. But this is more for, or this has been developed primarily for smaller platforms in the past, and it has limits in terms of how much memory it's allocated, how big your application can be, and also in the way how you interact with the DAL. It's basically a technology we have for many, many years. And 2 years ago, we launched actually the successor of that, which is our software guard extensions, SGX. And SGX is actually a technology which allows application developers to run certain aspects of their application in a really secure manner. And we have a lot of customers in financials, for example, or in industrial and so on. And they have all sorts of use cases. Either it's IP protection. You don't want the algorithms to be exposed, so you put it in a TE. Or we have software licensing, where people want to make sure that certain aspects of the software are licensed, and if they're not licensed, they don't run. And the licensing itself is happening in the TE, so that all the certificates used to basically enable functions are not exposed to anybody. And the really great thing about SGX is that all the data being used are encrypted on the entire platform. So even hardware-based attacks, for example, memory, cold boot attack, rip out the memory and try to reconstruct the keys, which are usually in plain text in the memory or as a bit stream. In SGX, they are encrypted. And only the CPU holds the key to decrypt. So it's very, very mature and secure technology we are providing here. And this comes with many of our silicons, and the SDK, which is then used by the developers, is all open source. Just go to our website, you can download the SDK with sample code, with also access to our experts, which help you to get jump started. So we really try to make sure that people use it. It's always about how you consume better what we already have. Because these technologies exist in our silicon for many years. It's not that they're all new. Like DAL, I think we talked about 10 years ago the first time, and SGX, I think we released it 2 years ago on our or 3 years ago on our very first silicon, and now it's across half of our portfolio at minimum. So the technology is there. It's all about how you guys make use of it. All right. And now I'm switching gears to the other side of the coin from what's in the platform and how you can consume it to two services we are providing. One, from end-to-end perspective, is around device management. We heard about it already a lot, that you need to manage the device, you need to take care of the life cycle, because the device is going to sit there for many, many years. So you need to deploy software updates. For sure you have to. You have to rekey the device in case of your certificates expired after 10 years. Have you thought about how you replace those? Well, many did not. They said, well, it may not last for 10 years. But if it, then we think about it. Well, that's the wrong answer. The right answer needs to be, well, I have a device management system in place which gives me the scale to what IoT is supposed to grow in terms of volume. And it gives me the functions I need for my particular IoT use case, which is around firmware update, software update, and this all done in a secure way with signed updates. And we heard in other sessions, at least I was in some other sessions, and signed updates, secure updates sounds easy, but there are many companies trying to do it, and it's really a challenge. Because there are a lot of things you need to take care of, not just only from delivering the signed images. You need to sign them somewhere, you need to validate them, you need to store them and distribute them in a scalable manner. And so that's what we do through our WindRiver Helix Device Cloud. So WindRiver is for many years, a 100% subsidiary of Intel, but still stand on its own brand, let's say. And Helix Device Cloud is that extendable framework for device lifecycle management. It doesn't do, in brackets, much more than device management, but it does device management really, really good, because that's what the focus on that platform is. We don't want to compete with Amazons and Googles and others on data processing or artificial intelligence and other things with this platform. This platform is really for device management. And it also scales in terms of horizontal and vertical. So you can use this on traditional Windows boxes, but you can also run this on a sensor, 16-bit sensor, 8-bit sensor. It does run there as well. It has limited capabilities because you don't need all the features on a 16-bit controller, which does do some sensing. But if you have a 64-bit Intel platform running a fully fledged Linux, then you need many features. And so that's the scale the platform provides in terms of vertical integration and horizontal in terms of features. It's also extendable, again, to the point it needs to be consumed by the industry. So it has a rich API which allows you to integrate it into whatever you have. We have a lot of customers where Helix Device was never seen. It just runs in the background and it's totally restified. And so any connection is done by their whatever platform through REST interfaces. So that it's really about consuming the capabilities easily. All right. The last piece is really on our secure device onboarding system, Oh, sorry, the text moved around here because of the font issue. But anyway, secure device onboard, really, the problem we solve is really around automating how a device is onboarded into its service in a very secure way, and most importantly, when it's need to be onboarded, not when it lies in the storage. So as I said at the beginning, if somebody who was at take Vodafone again or BT buys those 50,000 gateways, Dell is going to take care of this first part. So we're going to take care of Intel Apple. That's what we put into the silicon, or our partners if it's a non-Intel platform. Then we have our hardware capabilities like a TEE, which makes sure that this process runs in a secure manner. And then Dell manufactures those devices for all customers the same. But when BT gets those devices, they don't need to open it up and to provision it to their final usage. They can just take them and as they are, or tell even Dell to send it straight to their end customer. And the end customer only needs to switch it on. And then we're going to have a process which is very much simplified here. There's a lot of cryptography in the background happening, and a lot of attestation and verification and so on. But we do the matchmaking. We basically have a methodology implemented which allows the platform provider, which is BT, for example, to import an ownership proof. It's a digital ownership proof, cryptographically. It's not a piece of paper. And use an SDK from our platform to tell our onboarding system that I'm the new owner. I own this bulk of 50,000 devices. Regardless when they had been manufactured, or if they are in the sequence, or if they are just whatever time they had been developed. As long as they are SDO enabled, secure device onboard enabled, the user will switch them on. The device will go to our service in the cloud and say, well, here I am, tell me what I need to do. And we will know, well, this device belongs to this owner. And then we will send the device to that new owner, and the new owner and the device will mutually authenticate each other. So they really build trust between each other. The device knows this is my owner, and the owner knows this is my device. And if something is failing there, there's no connection going to take place. This prevents that supply chain is compromised, that there are devices in your inventory which are not belonging there, because you got this bulk of devices with an ownership proof from Dell. So Dell manufactured those things for you. And if you got another bulk, then it might not be your device, or they had been changed. And then the platform provider is basically provisioning the secrets which previously had been provisioned manually through that secure pipe with this trust in place. So you then provide keys, certificates, scripts, entire software packages, or an entire image. So for example, Microchip is using this process for some of their sensors, and they deploy an entire image. So they have just a micro or a very small software running on the sensor, which is just doing onboarding, and the actual sensor image comes comes just in time. And the customer just takes it from there and don't need to touch the device, touch the sensor, configure something. And the sensor will then connect to its destination, whether that's a LoRa system, or that's a Wi-Fi access point, or it's an LTE network, or it is Amazon. Wherever it scales to any sort of connectivity you want to use there, depending on how the device has been implemented with that technology. And so from technical viewpoint, this is just one layer down. We can go 10 more, which goes into weeds, but we don't have time for that, unfortunately. But this is basically a BT platform, for example. They're using one of our APIs to connect to our onboarding system. Within the device, there is our EPID key and the necessary SDK. There's a little client, basically a couple of kilobytes, which runs there on the TEE. And this 1, 2, 3 step basically is the actual ownership process. And then we are handing the ownership transfer off to the management system and the actual management agent. So that's an Azure agent, or an AWS agent, or a BT agent, or whatever agent. And they then exchange, or they setting up then their final connections. And through this process, you really make sure that the device is onboarded properly without user interference. And this is very fast. So normally, if you do this all manually, it takes a lot of time and money. This is done in seconds. And there's another very important topic which came into my mind as I was listening to some of the panel discussions and also some of the sessions, which is around how you reset a platform in case of an incident. It's not a matter it's not a matter how that incident is going to look like. It's just a matter when it comes. With this long lifetime and with this type of device, there's always a likelihood. And so what this implementation also allows you is really a full trusted compute base reset, the TCB reset as we call this, which means that if your device has been compromised and you want to build the trust up from the ground again based on new secrets, then this is the solution which gives you that, because it does perform an entire TCB reset on hardware level at a very low level before anything else runs. And so you can reset the whole thing and say, well, I want to run this process after 10 years again. And then I provision entirely new material, maybe new crypto, new hash values, maybe even other software components to bring the device to the state-of-art security it needs to have in this point in time, while other solutions may do this in software. But we can do this really on hardware level. So that's a very important point as well. All right. So I have one last slide, which I wanted to share, which is basically the question I always ask myself at the end of the day, how all this comes together. And so I brought an example from digital surveillance and security, which is a camera. If you are sitting in the front row, you can see the name of the vendor of doing that. But that's an Intel-based camera running our latest silicon. And you see they're utilizing those 7 things in those cameras to mitigate many of their issues. Not all of them, but many. So they use bootguard to initialize the BIOS properly. Then they bring on the device into a known good operating system. They're using our security API within their own software to generate keys, store keys, use the security capabilities. They use Helix Device Cloud to maintain the camera over lifetime. So they roll out patches, roll out updates, do all sorts of lifecycle processes. They're using our firmware TPM to store the secrets on the platform instead of having a discrete DPM. Saves a couple of dollars on the BOM and one end side. And they're using our acceleration. So ASNI is just one of the examples. They're also using others like ECC, for example, and SHA-NI accelerators, because they're using those algorithms within their platform to create, for example, to encrypt the video stream which goes off the camera. And in order to do this, you need fast encryption. So that's what we accelerate through our platform. And so this is a very good example of how our different technologies and capabilities in our platform and in the systems on top of it are consumed in a real IoT relevant product. And unfortunately, cameras have a bad reputation nowadays due to all the attacks which took place. But this is a good example of how you can implement and build a camera which is prepared to be secure in the next couple of years and has the capabilities to scope with the time and the day when an attack takes place. Because you have many different things you can utilize on whether you do a TCB reset and onboard the system again. You have Helix Device to roll out updates and patches. You have all the acceleration in the platform which gives you this assurance that you can run all of this. You have a secure storage for keys on whether they are today or tomorrow new keys and so on. So this is really good example from our end. And there are many more I could bring, but I thought this is an interesting and good example of how this comes together. With that, I made up the time we lost because of coffee and cake, so I open it up for questions and can take it from there.